Hey gang, welcome back. Today we're talking about something that's a little bit tricky, failure theories, and I'm going to see if I can't explain this in a way where they're not so scary, okay? So when we're talking about failure theories, first off, what is a failure? Now for us engineers, anything that's a failure, what you think about is if I have, a sample of material, and then once I pull on it too hard, pow, it breaks, right? And now I have two pieces. And we consider that to be a failure. But is that necessarily a failure? As engineers, we don't I can't think of a whole lot of things that we design that are meant, look at that piece there. Can you see the center of it? Okay. The center of this is deformed, right? This has been stretched hard enough that this has yielded, right? It didn't go back elastically to where it started from. Is that a good thing? Can you think of anything that's supposed to yield and not go back and then we can reuse it again? I don't know. So failure for engineers does not necessarily mean ultimate strength, right? Or not ultimate strength, but fracture, right? Two pieces. Failure to us can mean it has gone into the yielding portion of the curve there, and it is elastically stretched beyond where it can't go back to where it started from. So generally as engineers, that's a no-no, right? We don't want that. We don't want it to be permanently bent, okay? So failure here, when we say failure theories, you'll notice that we deal a lot with sigma y, which is yield stress, okay? So we need to stay below yield stress in our designs. Now when these specimens do fail, remember, you have a couple of things. Typically, brittle materials, right? Brittle materials, when they fail, will fail on a 45-degree angle plane. Look at that, 45 degrees, right? That's from shear. Where does shear maximum occur, right? Well, remember, in Mohr circle, we got to double the angle, right? And tau max is at the very top of the circle, right? Which is 90 degrees, but in the real world, that's 45 degrees. So at 45 degrees, that shear stress is the very highest, and when it shears in half, look at that. It tears on a perfect 45-degree angle. Isn't that cool? Now for ductile materials, they don't tear exactly like that on a 45-degree angle. I don't know if you're going to be able to see this or not. Maybe. I've got a few examples here. This one's a little bit better. They fail on what's called a cup and cone failure, okay? So I don't know if you can see this or not, okay? But one side of this specimen fails in a little V-shaped cup, and the other side of the specimen that pulled apart has a little V-shaped, the negative part that goes into that, right? These are all little test samples that we pulled apart in the lab, okay? This one has a pretty nice, it's a little piece of aluminum, pretty nice little cup in there. But anyway, what's happening there? Well, really and truly, it's failing on a 45-degree angle too. That cup has 45-degree angle sides, right? But it has it in all directions at the same time. And that's what makes that little cup in there as that fail. And once we learn Mohr circle, that where tau max is straight up and down, it really makes sense that, hey, the shear stress is the greatest at 45 degrees. And so when you look at these failures up close, they start to make sense, okay? And so what you've got here, what I have is a pocket full of broken parts now, okay? Anyway, so we're going to talk about some of these failure theories, okay? And we have basically two families of these failure theories. One is for ductile materials. That would be the Tresca and the von Mises, okay? And the third would be the Rankine, and that would be for brittle materials, okay? We're going to talk about both of those, and then we're going to work an example problem that uses these failure theories to tell whether we think a part would fail or not. And remember, fail does not mean break in half. Fail means I've exceeded yield strength, okay? So the Tresca failure theory is also called the maximum shear stress theory. These two things are the same. So Tresca and maximum shear stress theory, same thing, okay? Henry Tresca came up with this. And he says this, that sigma 1, the absolute value of sigma 1 is equal to is sigma yield, okay? Now, this is, what is sigma 1 and sigma 2? What is that? That's principal stress. How are we going to get principal stress? This sounds like the perfect job for a Mohr circle, doesn't it? Because we can get those two principal stresses, and then what this is basically is doing, it's comparing the principal stress to the yield stress. If this guy is bigger than the yield stress, then we have a failure. If this guy is smaller than the yield stress, then it's not going to fail, okay? So this really isn't an equal. It should be a less than equal to there. And then why is it sigma 2? Why are we checking that? Well, remember, when we have Mohr circle, let me draw you a picture. Sometimes we have Mohr circle like this, okay? Here's sigma 2, here's sigma 1, okay? Who's biggest? Sigma 1, right? Sigma 1 is biggest. It's the absolute value of sigma 1 is bigger, right? But what happens if my circle is over here on this side of the axis? Now, here's my sigma 1, here's my sigma 2. Who's biggest now if we're talking absolute value, right? Well, now sigma 2 is a bigger number, right? So sigma 2 is we would use that. Basically, what is it? We'll use sigma 2 when Mohr circle is on that side, and we'll use sigma 1 when Mohr circle is on that side. Does that make sense? So whoever's absolute value is bigger, that's the one we're going to use, okay? So I hope that makes sense of why that's that way. So that's why it says when sigma 1 and sigma 2 have the same signs, which means that that circle is completely that way. That's positive. When the circle is completely this way, that's negative, right? Then we would use that first option there, okay? Now if, down here it says they have different signs. Well, when would they have different signs? Well, that would be a Mohr circle that straddles the axis. Okay, here's sigma 1, here's sigma 2. So if you have a Mohr circle that straddles the axis, okay, then you have to do this. You have to take the absolute value of sigma 1 minus sigma 2 and compare that number to sigma yield. Again, if that's bigger than sigma yield, we got a failure. If that's smaller than sigma yield, it's okay, all right? This is the more conservative, this one here, the maximum shear stress theory of these two theories, okay, or these two theorems. Now, the second one, von Mises failure theory, better known as maximum distortion energy. Remember, when I have a material and I have stretched it, look at that, right? It's necked down there. There are little residual stresses left in the material. Those molecules got stretched, and now they're out of place, but they're still wanting to be back, right? So there is leftover stress in this part, right? It's been strain hardened. There's lots of things going on there, right? That's where that distortion energy comes from being stretched, from being distorted, okay? So when I use this theory here, how do you do that? Again, you have to have sigma 1 and sigma 2, so you have to have your principal stresses. So for all of these things, matter of fact, every one of them, the first thing you got to do is do Mohr circle and find those principal stresses, right? That's one thing you got to do right off the bat, okay? But this one says, take sigma 1 squared minus sigma 1 times sigma 2, and then plus sigma 2 squared, take that number and compare it to yield. Is that number bigger than yield? Then it failed. If that number is smaller than yield, it didn't fail, okay? Hey, future Hanson here. There's supposed to be a squared on this sigma y right there. Past Hanson left it off. Can you believe the guy? All right, back to the video. So here I have a couple of notes for you. It's used to predict torsion failures. This is the main theory that we use for things with torsion on them, okay? Because it's about, look, it says down here, it's about 15% better at predicting failure than this guy is, okay? So this is going to give you a more accurate prediction of whether a material is going to fail or not, about 15% better than this guy will, okay? Like I said, that's more conservative. If you want really a more accurate, you need to come down here and use von Mises, okay? So von Mises is just another theory, but again, these two theorems here are for ductile materials. And notice we use yield. We're comparing to yield for ductile. Now, if we think about brittle materials, right? Ductile materials, remember our stress strain diagram looked like that, didn't it? Okay. So on ductile material, this all of this up here is yielding, right? Yield, yield, yield. So a ductile material stretches and it's telling you, I don't like this, something's going on. It gives you a warning that there's going to be a failure. Whereas brittle materials, right, do something like this, okay? Brittle materials do something like that, okay? Now, on a brittle material, the thing we don't like about brittle materials is all of a sudden, they just fail, okay? And so they don't give you much warning that they're going to fail. Okay, so on a brittle material, we don't really have a lot of yield stress warning. So what do we do on the brittle materials? We look at this point up here, which is sigma ultimate, right? Because at that point, it just breaks. So brittle material, a fracture is the failure, right? We don't want that to happen, okay? So in ductile materials, we're looking for yielding. In brittle materials, we're looking for ultimate. And again, it's pretty much the same thing. This one, Rankine failure theory, is called the maximum normal stress theory. Again, used for brittle materials. You can tell that because of the ultimate, okay? And you just use sigma 1, if you're on that side, sigma 2 if you're on this side. Whichever one of these two is bigger, whichever one's bigger of the principal stresses. So, and again, due to imperfections in materials, brittle failures are hard to predict. Use with caution, okay? Because in brittle materials like cast iron, glass, right, there's imperfections in the material, there's imperfections in the crystalline structure, there's a lot of things that in the casting, there's a lot of things that couldn't be just perfect. And these numbers here are assuming kind of as close to a perfect material as you can get. So, if you're gonna use these numbers and say, okay, I'm gonna design something for that number right there, which is right at ultimate, it's probably dangerous, right? Because you're probably gonna have some imperfections that's not gonna be quite that strong. So what do we do with those? Hey, do you remember? We use a factor of safety, don't we? We'd want to put a factor of safety with these to make sure that they don't fail. Because we don't want to design something that's going to be right at yield. We don't want to design something that's going to be right at ultimate, okay? We want a factor of safety so that we can back that up, okay? All right. I see that my students have been in here, and Mandy thinks that I'm super cool. So, thanks a lot, Mandy, okay? All right. So let's see if we can work some problems using these theories over here of failure and see if we can predict whether these are going to fail or not. All right, let's try number 1 here. We have a piece of cast iron. It's cast iron. What does that mean? That's brittle. Yeah, it's brittle, okay? They give us the ultimate stress is 20 KSI, has 400 pound-feet of torque on it, okay? Find the smallest radius in the cast iron shaft that it does not fail due to the maximum normal stress theory, which is this one. Hey, that's the one for brittle materials, cast iron. Hey, all right. Okay, so if you're a little piece of material right there, right, little stress element, if you will, what are you feeling, okay? Well, is there anything stretching you? P over A? No. Anything bending you? MC over I? No. Is there any shear forces? Transverse shear? No. Is there any TC over J? Torsion shear? Yes, there is, right? Okay, so here we go. Now, we don't know the radius, okay? So the radius, let's just call him R. Okay? So tau, right, tau is equal to TC over J. Okay. So T, what is T? Now, Johnny Weak Sauce, is he in the house? Johnny Weak Sauce would say, yo, that's got 800 pound-feet of torque on it. 400 there and 400 there. No, Johnny Weak Sauce, no. It's only got 400, right? Remember, this 400 causes that 400 over there. Remember, if I section it in half, if I just look at half of it, how much torque is on there? Only 400, okay? So here we go, torque, 400 pound-feet. Now, got to be careful, because I'm thinking this radius is going to be in inches, and that's in feet. Let's get rid of that feet up there, okay? So let's going to multiply that by what? Let's get feet on the bottom is 12 inches on the top. That'll get rid of that guy. Times C. What is C? The distance from the neutral axis to the outside of the part. Okay, in this case, it would just be R divided by J. What's J for a solid round shaft? That would be pi over 2 R to the fourth, right? All right, and so what can we do with that? Well, here's what we can do with that. Tau is equal to, let's do a little math here. Let's math this up. 400 times 12, 400 times 12 equals, and then divided by pi over 2, pi divided by 2, parentheses, 3055.77, and then divided by what? One of those r's is going to go away, divided by r cubed. Do you agree? Okay, so that's tau max. That's the biggest shear on that shaft is tau max, okay? Now, if we were to draw Mohr's circle, okay, we already said there was no sigma stress, there was no MC over I, there was no P over A, which means what? That sigma at 0 for that guy, all it has is shear stress on it, right? So all it has is a number here and a number there, right? Which is, that number is 3055.77 over r cubed, right? Remember, this is tau positive down here, this is tau negative up there, this is sigma, right? Can I draw a circle out of that? Well, yeah. Goes like this. Kind of circular. What does that mean? If tau is that number, what does that mean sigma 1 is? Sigma 1 is, that's a radius, right? That means sigma 1 is that number. So sigma 1 is equal to 3055.77 over r cubed. And guess what? So is sigma 2, right? They're the exact same thing. So if we want to find out what it can take, then we should just set this equal to what? Right? What does this say do? It says take sigma 1, which is that, and set it equal to the ultimate stress, okay? So let's try that. The ultimate stress is 20 KSI, okay? So this is going to be 20, oh, don't fall for that little trick, KSI, that's kips, right? 20,000 pounds over inches squared is equal to T, which is what? No, it's equal to T. It's equal to sigma 1, is equal to that, right? 3055.77 over r cubed. So r cubed equals 3055.77 divided by 20,000. So r is equal to, here we go, divided by 20,000 equals, and then second cube root. Oh, Lordy. All right, I forgot how to put that in my calculator, but I figured it out. And r is equal to 0.535 inches. Okay? There you go. So for that not to fail, it needs to be at least 0.535 inches or bigger, right? It can be bigger than that, but that's as small as it could be right there, okay? So that's the answer to number 1. Number 1, R equals 0.535 inches. Well, that's not too bad. Let's see if we can do number 2. Okay, here we go. Number 2 says this. Will the specimen fail due to maximum shear stress theory? Wow. Now it's A36 steel, okay, the steel specimen, and so guess what? We're talking about a ductile material here. So will it fail due to maximum shear stress theory? I erased the brittle theory. There, that's this guy. And then it says, will it fail due to that theory, right? So we're going to test it using this guy, then we'll test it using that guy. We'll see if they give us the same results or not, okay? So this is kind of a combined loading problem to start off with. Look, I got a specimen here that has torsion on it, and it has a load on it, a compressive load. Again, if I was that little stress element, because I like to think of that little stress element because that's what I'm going to use my Mohr circle to transform, right? So if I'm that little stress element, here I am, what am I feeling, okay? I think I'm feeling a compression. I think I'm feeling a P over A, don't y'all? All right, so what do we got here? So sigma equals P over A equals what? 15 kips divided by A, which is pi times r squared. And r is, it's an inch diameter, so 0.5 squared. What is that equal to? 15 divided by pi equals divided by 0.5 squared equals 19.01. 19.1. And that's going to be what? That's KSI. Now I'm going to be okay. I'm going to leave that in KSI because guess what? My sigma yield that I'm going to compare it to, it's in KSI. So I'm kind of happy with that. So here's what I've got. If I'm that stress element right there, whoop, here I am bigger. I have 19.1 KSI on me, okay? Now how much, do I have any shear on me, right? Do I have any of this business going on? Okay, and again, let's see, up, down. How do I do that? I break this in half, right? Break this in half. There's the mole stress element. This guy on this side is going down. So on this side, it has to go up. On this side, down. On this side, up, right? I'm just working out the direction of shear. Although it's not important on this problem, it's just good practice to figure out the correct direction of shear. So that little stress element would look like that, right? There's a little stress element A, and there's stress element A. Oh, this is a lot, isn't it, gang? We got it, though. We're almost there. So let's figure out what is that tau. So tau here. Again, this is a TC over J, isn't it? Okay. The torque, 3.25 inch kips. 3.25 inch kips. Okay. Times C. What is C? The distance from the neutral axis to the outside of the part. That's 0.5. 0.5 divided by J, which is pi over 2 times r to the fourth. Okay? And that's inches to the fourth. Okay? Let's see what that gives us. So 3.25 times 0.5 equals divided by 0.5 to the fourth equals divided by parentheses pi over 2. 16.55. So all that is 16.55. And that also KSI. Okay. 16.55 KSI. Okay? You with me so far? Combined load problem, create a stress element. From my stress element, create a Mohr circle. Okay? So I need 2 coordinate points, right? Here's the X face, there's the Y face. Okay? On the X face, what do I got? I got 19.1. Oh, but it's negative. On the Y face, I got 0. On the tau, on my X face over here, it's rotating me negative, right? So clock above, this is going to be negative 16.55, and this is going to be positive 16.55, okay? Y'all remember how to do that? There's a million more circle problems I've got on here. So You go back and review that if you're lost there. Okay, let's plot these. Let's plot them. Here's my Mohr circle. Okay, here's tau, sigma. This is positive. This is positive. This is tau negative. Okay, and the first point is negative 19.1, which is there, and negative 16.55. That's there. The next point is 0 and negative, which is there. So there's my deal here. Okay, imagine that making a whole circle there. Okay. So what do we got? Let's see. From here to here, so on our circle, this is 19.1, and this height here, 16.55. This height here, 16.55, which means that this distance here, it's got to be half of 19.1, doesn't it? Which is negative 9.55. Okay, so let's calculate our radius, which is 9.55 squared plus 16.55 squared, square root, 9.55 squared plus 16.55 squared equals second, square root second, answer equals 19.10. 19.10 KSI. And guess what? That's tau max, isn't it? Okay. And remember, sigma 1 and sigma 2 are equal to what? The center point minus 9.55 plus or minus, right? Sigma 1 is plus a radius, sigma 2 minus a radius, right? So 19.10. Okay, so here we go. Sigma 1 is what? 19.10 minus 9.55. 9.55. Sigma 2. Sigma 2 is what? 19.10 plus 9.55 equals 28.65. That's KSI. That's KSI, but this one is negative, right? Sigma 2 is negative, isn't it? Okay? All right, here we go. Let's use our maximum shear stress theory. Bam, that's what they want to do first, right? Do we have the same signs? Well, sigma 1 is positive, sigma 2 is negative. No, we don't have the same signs. So then what does that mean? We need to use this guy, okay? Sigma 1 minus sigma 2. So sigma 1, 9.55 minus sigma 2 minus 28.65. And we're going to compare that to what? To sigma yield, right? Sigma yield is, was that given? 36. Okay, remember, if this side is bigger than 36, we got a failure. If this side is smaller than 36, we're okay. Okay, so here we go. Now, minus of minus, that's going to be plus. So 9.55 plus 28.65 is 38.2. Which is, guess what? Greater than 36 KSI. So what do we got here? Wah, wah, wah. This failure theory is predicting that that thing is going to fail, right? It's going to fail. Now, it's pretty close, right? It's pretty close. On these ones that are pretty close, you might want to check it one more time with the other theory and see what it says, okay? So let's try the other theory, which is the von Mises failure theory, or the maximum distortion energy theory. It's just sigma 1 and sigma 2. We already got that, don't we? There's sigma 1 and sigma 2 right there, okay? Now we're going to take that and compare it to yield and see if it fails. So let's do that. So sigma 1 squared is 9.55 squared minus, okay, sigma 1, 9.55, times sigma 2, negative 28.65. Again, minus and a minus, going to turn that into a positive, plus sigma 2, 28.65 squared. But it's negative. I'm squaring it, okay? Get off me. God. Equals, here it is, 36 KSI. Okay? So is this failure? Is this going to be bigger than 36? It's going to say fail. If it's less, we're okay. All right, so let's go. 9.55 squared plus 9.55 times 28.65 plus 28.65 squared equals 1185. Oh yeah, I forgot one thing. I forgot something. This has to be squared right there. Right? This has to be squared right there. So 1185. Oh my gosh, Hanson, come on. 1185.63, okay, is equal to 36 squared. So let's just take the square root of both sides. So 36 over here, and what's the square root of that guy? Second, square root, second, answer equals 34.43. Guess what? That number is less. So this theory over here, this one over here says, hey, it's okay. Just barely, but it's okay. This theory up here says we're going to have a failure. So be careful. This is more conservative, remember? This is more conservative. This is 15% better, especially on torsion problems, which is what we have here, right? Now again, if you're my engineer and you're working for me, I don't want you to be this close to the limit. I need a little factor of safety in here, right? But anyway, that's how you use these theories, okay? All right, I hope this clears up some of your muddy thoughts. I'll see you next time.